Hi there, I'm NZ Guy, and today I will present WINGMUZZ black box testing of IoT protocols via two-dimensional fuzzing schedule. This is joint work with 小刚珠、恩泽代、小涛冯、邵华王、辛夏、盛文, Kwok Yen Lan, and Yang Xiang. The core question we ask is, how can we guide black box fuzzing of IoT protocols when source code and rich runtime feedback are unavailable? Our answer is, leverage open source implementations of the same protocol as WinMates and coordinate a two-dimensional schedule that guides black box fuzzing more informatively. Let's start with the motivation. On the left, we see the scale, billions of connected devices and a steep rise in attacks. IoT systems are a broad and moving target. In practice, black box fuzzing is often our only option for priority devices. No source code, no firmware access, limited execution feedback, random mutation with coarse or no coverage guidance. This makes exploration inefficient. Our key observation, highlighted at the bottom right, is that developers often publish open source implementations for the same protocols. If we can learn from those, perhaps we can better guide the black box fuzzing of the closed target. So, the idea is simple. Use the runtime feedback from gray box fuzzing on open source protocols to guide the black box fuzzing of the target device. Gray box fuzzers give us coverage and other signals, but black box on a real device does not, so we bridge them. Okay, why does this work broadly? Because 85.5% of IoT protocols have open source implementations. That's a huge opportunity to reuse structure and behavior as guidance. For example, we listed like 89 protocols, and we found 61 of them has the open source implementations. Here is the WinMUZZ pipeline. On the right, we run gray box fuzzing against several open source WinMates. We collect the feedback and golden seeds from these runs. Then, on the left, we run black box fuzzing against the real IoT target, consuming those golden seeds and feedback guided inputs. The engine is governed by a two-dimensional schedule. The first one is the WinMate schedule, which open source implementations to focus on. And the second, seed schedule, it focuses on which inputs to emphasize. This cross-feeding lets the black box side benefit from the structure and learn from the gray box side. First, we see the WinMate schedule. We measure response similarity between the target and each WinMate using a distance over response factors generated from the same seed corpus. More similar WinMates receive more fuzzing energy. We exploit their behavioral proximity to the target. And the second one is the seed schedule. We run coverage-guided fuzzing on the selected WinMates and maintain a shared seed pool. Golden seeds, those that unlock new coverage, are promoted and shared. We prioritize low frequency or novel seeds and allocate energy inversely to seed frequency, so underexplored behaviors got more attention. So what does this bias coverage across 8 protocols listed from the SIP to DICOM and the DTLS? WinMUZZ improves age coverage roughly from 12% to 42% over the representative baselines on average. So better guidance translates into broad exploration across diverse protocols. And we also do the ablation studies. Our ablation disables one dimension at a time. Without a WinMate schedule, performance drops more than without the seed schedule. So the conclusion is choosing and emphasizing the right WinMates is the bigger lever, while seed scheduling is still helpful. So there's another question, how to select WinMates. There are two practical guidelines. The first one, selection strategy. Our hybrid strategy has the best performance. That's to say, in black box setting, diversify implementations. Hybrid strategy tends to increase the chance of including a close match or a close wingmate. Number of wingmates. The box plot on the right shows the coverage improvements versus time and wingmate count. Conclusion is, longer rounds can afford more wingmates. When time is short, reduce the wingmate number accordingly. Okay, but our final goal is to find bugs or vulnerabilities. So we do the experiments in the emulation setting and the real-world setting. In the emulation setting, WinMUZZ found 10 vulnerabilities, and it achieves the best time-to-bug performance in 9 of them. For the only one, CVE 2019-8936, Buffaz discovers it faster than WinMUZZ, but only 9 minutes faster. This is because WinMUZZ's communication mechanism. It communicates with the wingmates at 1-hour intervals to allow them to provide high-quality seeds to the black box side. As for the real-world setting, WINGMUZZ exposes a new vulnerability in BMW NBT Evo and a new one in the GL-INET Smart Router. Okay, to summarize, WINGMUZZ leverage open-source wingmates to guide black box IoT fuzzing through a two-dimensional schedule. We achieve substantial coverage gains and uncover real vulnerabilities on both emulated and physical devices. Thank you for your attention. Happy to take questions.